السلام عليكم ورحمة الله وبركاته. يسعد صباحكم ومساءكم. المرة الماضية وصلنا لحد هذا السلايد وحلينا هذا السؤال. هذا السؤال كان هو نهاية chapter 1. Now we'll move to a new chapter which is chapter 2. In this chapter we'll talk about energy and first law of thermodynamics. Okay? Energy and first law of thermodynamics. So first of all, we need to define or give you certain terminology. Okay. So how does energy, and we'll start with this question, how does energy cross a closed system boundary? We answered this question before. So here is system, and this system is closed. Okay. What do you mean by closed? Closed, there is no mass in, mass out. Only energy can cross the boundary. Energy in terms of heat, Q, or in terms of work. Okay, this is the most important energy we care about. Okay, so energy can cross the boundaries of a closed system in the form of heat and or work. Okay, so how does energy cross? Either cross it as heat or as work. If the energy transfer across the boundaries of a closed system, is it due to temperature difference? If there is temperature difference between inside and temperature outside, there is temperature difference, or delta T does not equal 0. If this is true, this is the meaning of the sentence. If there is temperature difference, then we can refer to this energy as heat. So anything related to delta T, related to temperature difference, we can name this energy as heat. Otherwise, it's work. So anything else except delta T, we can say that this is classified under work. Okay. So what do we mean by heat? What is the definition of heat? Heat is defined as the form of energy or thermal energy that is transferred between two systems or between system and surroundings by virtue of temperature difference. Okay, so simply we can summarize it as heat is defined as energy transferred due to temperature difference. That's it. Okay, so this is the most important word, temperature difference. Heat is energy in a transition. It is recognized as it crosses the boundary of a system. So here, for example, 2 kilojoule transfer out of the system as a result of temperature difference. Okay. If we have no heat transfer, no heat crossing the boundary, okay, we can name this system as adiabatic, and we can name this process as a adiabatic process. Okay. Remember in the last chapter we said we have isothermal process, isochoric process, isobaric process. Okay, and now we have adiabatic process. Okay, so what do you mean by adiabatic process? No heat transfer. So this process, adiabatic, a process during which there is no heat transfer, is called adiabatic. So no heat transfer crossing the boundary. See, either we said the Q entering the system or leaving the system, the Q equal to 0. Nothing happened. Okay. When we can say a Q cannot crossing the boundary if we have insulation. And here we have a very important notice. Once we said adiabatic process, that does not mean we have isothermal process. Okay, this is completely different. So if we have isothermal process, it does not mean that we must have adiabatic. Okay, and once we said that we have adiabatic process, that does not mean we have isothermal process. Maybe one of you could not understand it very well. Okay, I will explain it one more. So for example, if we have a boiler, okay, we have a boiler, and this boiler we have a set point T equal to 100 degrees Celsius. So this temperature will remain the same, but at the same time we have a Q lost from the system to the surrounding. Okay, but temperature, this constant temperature, we can name this process as isothermal. Isothermal, when it reach 100 and remain constant at 100. Okay, but at the same time we have a Q escaping, so this is not a diabatic process. Okay, the temperature constant isothermal, but Q can escape to the surrounding. Okay, this is example of isothermal. Okay, now example of adiabatic. This example, very good example. Adiabatic system, we don't have any Q crossing the boundary, but at the same time, the temperature inside the system between 1 and 2 may vary. Temperature will not remain constant. Why? Maybe you have chemical reaction inside, so the temperature will raise. Okay, so isothermal, T constant, and very good example is boiler. Okay, so this is isothermal scenario. Adiabatic process, Q crossing the boundary equal to 0. Symbols of heat, we'll have three symbols, either Q uppercase, Q lowercase, and Q uppercase with dot. Okay, so Q, either I'll use this symbol or this symbol with this subscript. Okay, 1 to 2. 1 to 2 means the process. We have this state 1, starting state. So let me erase it. 1 means the starting point, starting state, and 2 means the ending state. This is end state. Together, once we write them together, it means we have process. Okay, so Q uppercase without any dot is the amount of energy. Okay, amount of total heat transferred during process 1 to 2, and its unit, once it is amount of energy or energy, it is kilojoule. This is in SI unit. And British unit, this is BTU, British thermal unit. This abbreviation for British thermal unit. Lowercase q is the heat transfer per unit mass. Okay, and its unit is joule per kilogram. Q dot rate. Once you heard that we need rate, that means Q dot rate, it is joule per second or kilowatt. Sign convention for heat. So here we have a system. Okay, and if this system gain heat from surrounding, then this is positive quantity. If this system lose heat to the surrounding, then this is negative. Simply. So إذا اكتسب حرارة بيكون positive. تكون الكيو اللي داخلة على السيستم بجمعها بعطيها إشارة بوزيتيف. إذا كان هذا السيستم فقد حرارة للسراوندينج، فقد، هي الكلمة اللي اسمها فقد، okay, فبعطيها إشارة minus. Okay, so heat transfer to a system. إذا إجت هيك في نص السؤال على طول بعرف إنه الكيو اللي عندي أو معطيني إياها السؤال حتكون positive quantity. إذا كانت from lost from the system, heat transfer from a system to the surrounding, so this quantity is negative. So what do we mean by work? you know very much that work equal to force multiplied by parallel distance. Okay, so if we have force and this force moving this system or this body at distance s, and both of them parallel, okay, then we can say we have work. So in order uh, to assume that we have work, we must have force and we must have displacement. Okay, work is defined as energy again, energy transfer associated with force acting through a distance. Okay, so we have two conditions, force and distance. Symbols for work, we have uppercase, we have lowercase, and we have uppercase with dot. Okay, so the subscript again, either we use nothing or we add the state names, and together they are process. So this symbol, it represents the total work done by or on a system. We'll see the effect of these two words on the sign convention. On a system during a process from state 1 to state 2. And remember, those states must be equilibrium. Okay, and its unit is kilojoule, same as Q, uppercase. So work lowercase, it is work per unit mass, and it is kilojoule per kilogram. W dot, directly we name it as power. Okay, it represents work done per unit time, and its unit is kilowatt or kilojoule per second. Sign convention. Now, if the work done on the system, work done on the system, then this work is negative. If the work done by the system to the surrounding, then this is positive quantity. Okay? So work done on a system, this is negative. Okay? If the work done by the system on the surrounding, so work done by the system against an external force or against the surrounding acting in the opposite direction of the motion, so it is positive quantity. Characteristics of heat and work. Both of them are boundary phenomena. It depends on the boundary. Interaction of the system with the boundary, with the surrounding. That is, they are recognized at the boundaries of a system as they cross them. See here, we care about this amount. So it is positive once it is across the boundary. Here, once it is enter from the surrounding inside, we give it negative. So it depends on, so they are boundary phenomena. It depends on the boundaries of the system as they cross them. System possesses energy. This is a fact. Okay, we have energy. Everything, every system has energy. Okay, not heat or work. Okay, we have energy stored inside the system. We do not talk about the boundary. Okay, and both are associated with the process, not a state. So whenever we talk about the state, we said that the system has energy stored. Okay, whenever we talked about the process, then during the process from 1 to 2, maybe we have some heat gained from surrounding or heat lost to the surrounding. The same for work. Both heat and work are bath function, as I mentioned in the previous point. During state 1 to 2, something happened, something crossing the boundary. either in terms of temperature, then this is heat, or anything else, this is work. Okay, so they depend on the bath, they depend on the process. Remember when we draw 1 to 2, then we draw a line. This line we name it as bath. Okay, so both Q and work depend on this bath and the function of this bath. That is, their magnitudes depends on the bath followed during process as well as the end states. So they depend on the end state and the bath itself. So what are bath functions? See here we have bath function and we have point function. Bath function have n exact differentials designated by symbol delta. This symbol. So integration. So if we have here, for example, B versus V, okay, and we move from 1 to 2, so we have process B and we have process A. And both of them, by the way, what? Expansion. Why? Because we are moving from smaller volume to larger volume. Okay, so we have two processes. Okay, now the Q and W depends on the path, depend on the process itself. Okay, so if we take the integration from state 1 starting state to the end state for then for the n exact differential W, for example, for the work, then this is equal W1 to 2. We could not write it as delta. So the correct thing is to write either W and drop the subscript, or you write W with this subscript. But this is not allowed because W depends on the path. It does not. We cannot say that here we have W2 and we have here W1. Okay, because it depends on the path. It does not depend on the state. It does not depend on the point. But this is valid when we are talking about point function. So point function have exact differentials designated by symbol delta uppercase. Okay, so if we are talking about volume, for example, then we can say we have volume 2 minus volume 1 or delta V. So at the state 1, we have certain volume. We have exact amount for this property. And on state 2, we have another exact amount of this property. So we can say yes, delta V. So as a general rule, properties are point functions. All properties, temperature, pressure, volume, mass, density, etc. Okay, but heat and work are path functions. Okay, so point function or properties point function. For example, pressure, I can say delta. I can say delta temperature. I can say that we have delta V. But path function, I can write either W or W1 to 2. But remember, if you write in the exam delta W, I will deduct mark from you. Okay, so this is not allowed. Types of work. We have mechanical work. We have electrical work. Okay, so in the mechanical work, the most important types is the moving boundary work, the second shaft work, and then we have spring work. Rarely we'll see those types. Okay, so this is the most common form in this course, the moving boundary work. Moving boundary work أحسن مثال عليها, the best example is piston cylinder. Okay, we have piston cylinder, and remember when we draw control surface, we call this control part of this control surface moving boundaries. Okay, so the name coming from here, moving boundary work, because we have one of the boundary moved to the left as a compression or to the right as expansion. Electrical work, so this is V multiplied by current multiplied by delta time. Then we can calculate the power, watt, here at dot. Okay, so for example, if we have a closed system and we have electrical current passing in this heater, then we can say here we have W added to the system, and this form is the W electrical. Okay, so this is heater. Heater means add heat. Okay, but we do not refer it as heat. We refer it as W. Okay, because the thing that crossing the boundary is electric. And how we calculate this power? By using this equation. Okay, then in order to find out the mechanical work, see, we are focusing only on the mechanical work, and the most important type is the first type. Rarely we'll see electrical work. Okay, then the two requirements of the first type were, when we talk about mechanical, okay, to exist is to have force as well as to have certain movement or certain displacement. So force and S, displacement. So if any one of them absent, then we don't have work. So work depends on force as well as displacement. For example, here, do we have work? Yes. Why? Because we have force and we have certain displacement. So if we calculate work, it will be, since this moved ds, then it is integration from state 1 to state 2, force multiplied by the displacement. Now if we divide by delta A and multiplied by A, if we divide by A and multiplied by A, then we can say that force divided by area, this is what? 1 to 2. This is pressure. Force divided by area, pressure. Area multiplied by ds, this is dV. And by the way, which area? This is a piston. If we take another view, we'll see this piston like this. Okay, then this is our area, cross-sectional area, circular. Okay, if this piston move this distance, then we are talking about volume. Okay, this one. So area multiplied by ds, it gives us pressure multiplied by volume. Okay, if pressure is constant, then B delta V give us the boundary work. And most of the time you will see that this work, I will give it this subscript, boundary. Or we can say W 1 to 2. Okay. So here, this piston, because we have force upward, then we have expansion. Then on a PV diagram, we have expansion from 1 to 2. Okay, 1 to 2. A certain distance, we call it ds. Okay, as you can see here. But this is here, we have dv. So in order to move from force and ds to pressure dv, and in order to account this change, we'll take the integration for f ds as I did earlier, and then multiplied by A divided by A. This term you can name it as pressure, and area multiplied by ds we can name it as volume. Okay, so this equation represents the general form of boundary work. So this is the definition. Integration P dV. Okay, and from this definition we can say that this definition, integration, represents the area under the whole curve, under the process. Okay, so it is integration. الانتجريشن it means area under the curve, المساحة تحت المنحنى. Okay, so who can tell? What do we have here? Process or cycle? Yes, we have three processes: process C, process B, and process A. Okay, because all of them directed from one point to another. So same thing for B, same thing for C. Okay. Now the other question: which process has the greatest work? All of them, by the way, expansion, because we are moving from lower volume to higher volume expansion processes. Okay, which one has the highest work? It depends on the area under the curve. So the one has the largest area under the curve has the biggest work. Okay, so you can tell from here that work A 10 kilojoule, work B 8 kilojoule, and work C 5 kilojoule. Now what do we have here? Cycle or a process? We have cycle. Why? Because we are starting from point 1, we move to point 2, and then we go back to point 1. Then this is cycle. Okay? Now, another question. Process 1 to 2, we name it B. What we can tell about this process? This process is compression. Why compression? Because we are moving from larger volume to lower volume. See here the arrow? Here we have an arrow. So process B, compression. What about process A? From 2 to 1, this is starting state and this is the ending state. And here is the arrow. Arrow on the process is very important, tells a lot. Okay, since we have expansion, since the volume increased, then we have expansion process. Now, imagine that we don't have the drum. Okay, now here, for example, 1 to 2. 1 to 2, I can draw a piston cylinder, and in order, this is 1, and here is the second state, state 2, so the volume decreased, and we have work applied from surrounding. Okay, so here the work done on the system in order the compression to be accomplished. Okay, so in order to move from 1 to 2, we need force coming from the surrounding. So here work done on the system. Once work done on the system, it means we have negative work. Okay. Okay. Now, on the other scenario, this is scenario process B. Process A, what do we have? We have compressed. Here, let us assume we have gas. State 2. And this is state 2, move to state 1. State 1. Then this is expansion process. The work done by the gas, okay, on the surrounding. Okay, then here we have positive work because work done on the surrounding. Okay. The cycle shown in the figure produce network output W net. Because here, this is the area under curve 1, okay, and it was negative, process B negative, okay, and here is process A, area under the curve, and process A is positive. So the network is the subtraction. If we add them together, we will add them and we'll consider the sign of each component, okay? So this is plus A because work done by the system on the surrounding, okay? Plus because we are caring about the net, the summation. But this one is done by the surrounding on the system, okay? Done on the system, so this is minus. Why the network here? Once we subtract them, we end up with this area, okay? Only this area. This is because work done by the system during expansion process is greater than the work done on the system during the compression. Okay, so here from writing you can tell easily. This is because the work done by the system during the expansion process. Expansion process we are talking about WA. So by the system positive. Okay. And always this is expansion from smaller volume to bigger volume. Is greater than, so this is greater than the work done on the system during compression. On the system, this is compression, and once it is on the system, minus, so minus WB. The difference between them, the two, is called the net, okay, the network during the cycle, or the clock area. So WA greater than 0 because we have expansion. Delta V greater than 0. Remember the general definition? B dV. Okay? From V1 to V, here WA from V2 because it is the starting point up to V1. So delta V positive, that means we have positive A. Or you can understand it from expansion. So either by applying this equation or from your understanding that V2 smaller, V1 greater, then we have, if we move like this, we have expansion. The other word, negative. Why? Because delta V, negative. Okay, delta V equal to integration from the start point, which is V1 to V2. V dV. Okay, and delta V or V1 greater than V2, then this will give us negative. This is using equation numeric. Now W net is the subtraction between both of them. Okay, because this one is negative and this one is positive. This is very important, by the way. It's very important to understand it very well. Moving boundary work for quasi-equilibrium process, and most of the time we have a quasi-equilibrium process or ideal. Remember when we talk about ideal or quasi-equilibrium process, we assume that pressure at any state along the piston remain the same. Okay. Strictly speaking, the pressure in the integral is the pressure at the inner surface of the piston, and this pressure along at each point remain the same. Okay. So it becomes equal to the pressure in cylinder only if the process is quasi-equilibrium. Thus, the entire gas is at the same pressure at any given time. So دائما حنفرضها إنها quasi-equilibrium process. Okay. Okay. I will end up up to this slide. Okay. So next lecture, I will start talking about how to compute work for some special processes. Okay. Up to that time, make sure you study everything, and we'll have a discussion on uh, Thursday, okay, at 10 a.m. See you then.